Now, what I want to do real quickly is review how to find them and then show you the Mathematica commands. Again, raise your hands. Has everyone had to find eigenvalues and eigenvectors of at least a 2 by 2 matrix? Good. So I don't have to take too long on that. We rewrite our eigenvector equation. Why do I rewrite it as a minus lambda I x equals 0? Well, I'm trying to solve for x. What is the obvious solution of this equation? Would be the 0 vector if the matrix A minus lambda I has an inverse, the solution is x equals 0. We don't like that. Well, I mean, we like it, but it's the trivial solution. We don't care. Obviously, A times 0 equals lambda times 0, lambda being 0. So that's not useful to us. There are useful solutions when this does not have an inverse. And that is something fundamentally different about matrices. That you go through this derivation and then quickly you have to actually find them and you forget about this step. But this is a mathematical concept we use in other places in physics, not just for the eigenvalue problem. We recognize that matrices behave fundamentally differently. That I can have two numbers that are not 0 equal 0. Because I'm not multiplying numbers, I'm multiplying a matrix and a vector to get a vector. So the 0 on the right just means all components are 0. And so I can have a matrix that's not got zeros, a vector that's not got zeros, but they combine because of the way matrix multiplication works to give me zeros. But that can only happen if the stuff on the left does not have an inverse. And when does the stuff on the left not have an inverse? When the determinant is 0. And so this is if and only if the determinant of A minus lambda I equals 0. And that's how we get the eigenvalue-eigenvector equation. The reason I emphasize it is we're going to talk about these for infinite vector spaces and functions later on. And you do it a little bit differently. But for finite matrices, this is the key thing. And you end up with an algebraic equation for the lambdas. And so notice the first thing you do is step 1 is solve for lambda. And then once you have lambda, you solve for x. So just to be specific, if we take the following fun matrix, 5 minus 2 minus 2, 2. I make the determinant of 5 minus lambda minus 2 minus 2, 2 minus lambda equals 0. So if I was, by the way, if I was doing this for homework and I asked you to do it by hand, you would get this far. You would say, well, we have the equation 5 minus lambda, 2 minus lambda, minus 4 equals 0. And then you would use solve in Mathematica. Again, with Mathematica, I don't expect you to necessarily solve these quadratic equations. However, keep in mind on the test, you won't have Mathematica. So obviously, you may want to remember and practice how to solve simple quadratic equations. But on the homework, if at this point you want to use solve, fine. Makes sense. If you do it, if you work it out, I picked a nice one. And so lambda equals 1, and lambda equals 6. Now I have my two eigenvalues. And it's an n by n matrix, so I should get 2. 2 by 2. Occasionally they're degenerate. And now I go back, and I take each one. And there's really two ways to do this. Some people like to plug in to the a minus lambda I equals 0. Some people like to plug into the ax equals lambda x. That's a personal preference. They're the same equation.
Should they be -1 and -6?
Oh, one of them is negative. You're right. Which one is negative?
I think they both have to be.
No, they're both, 1 and 6. It's x minus 6, x minus 1, so they're 1 and 6. Yeah. That's okay. I do that all the time. That's why I use solve. And here's the one point I want to make that I don't know why always causes trouble. So this matrix here is A minus lambda I. Notice we have two unknowns, and you think you might have two equations, but they're really the same equation. And I'm going to give you a warning now. I can't tell you how many people, when doing it by hand, get here and then spin their wheels trying hard to solve for x and y. I can't solve for x and y. I just have to pick x or y, one of them, and I always pick one of them to be 1 because there's a nice small number. If you're kind of masochistic, you could pick x to be 963.5 if you wanted. Perfectly valid answer for x, and then a weird number for y. But I pick a convenient one to be 1, and then I know the value of the other one. So x is 1, then y is going to be 2. And that's the step by hand that I think often causes the most trouble. Because remember, the eigenvectors are a direction. It's not a unique vector for each eigenvalue. It's a direction of eigenvectors. There's an infinite number of them. And so I would get x equals 1, which would imply in this case y equals 2. So for lambda equals 1, I get the vector 1, 2, which I can make normalized. And be 1 over root 5, 2 over root 5. Normalizing it is about as unique as you can get. On my tests, if I don't specify normalized eigenvector, you don't have to normalize it. There are some applications of the vectors where they need to be normalized. So if the question is about an application of the vector where it needs to be normalized, then yes, you have to normalize it. For the lambda equals 6 case, I'm just going to give you the answer. The second eigenvector turns out to be minus 2 over root 5, 1 over root 5. In this case, the eigenvectors happen to be orthogonal. Now, let's look at quickly some of the Mathematica behind that. Take a deep breath, shake out, yeah, you know. So I'm using the same basic matrix here. I'm calling it M1. Now, I'm going to do a couple of things with this, because I'm going to show you now the change of basis as well real quickly. Oh, actually, no, I'm just going to show you the eigenvector stuff, and then we'll come back to the Mathematica file. So for future reference, we're going to use this test vector for something. And what you can see here is what I'm doing is I have a vector 2/5, 3/5. I multiply by m1. That's what m1 does to the vector. Now, in computing eigenvectors and eigenvalues, you kind of have two choices. There are 3 Mathematica commands. Eigenvectors will give you just the eigenvectors if that's all you want. Eigenvalues will give you just the eigenvalues if that's all you want, in the same order. So this eigenvalue goes with this eigenvector. Notice it makes no attempt to normalize them. I can do the system, in which case you get the first element is the eigenvalues, the second element is the eigenvectors. And notice Mathematica's use of brackets is very handy here. If I want this element, I would do bracket just 1, and it would pull out these two things. If I want this one, this is the first and then the first. So I would do 1, 1. To get down to here, I have to do 2, 1, 1. So let me just show you that real quickly. So if I do %6, %6 bracket 1, I get those pairs of eigenvalues. If I do bracket 1, 2, I get the second eigenvalue. If I do %6, 2, I get my 2 eigenvectors. If I do 2, 1, I get my first eigenvector. If I do 2, 2, I get the second component of the first eigenvector. And so this bracket notation is very flexible. This is no normal matrix that you would think of, because its dimensions are all kind of weird. Right? If I tried to do 1, 1, 2, it doesn't like it, because the first element only has 2 elements in it. So I can't use a third index on the first element. The other thing I wanted to point out, I had mentioned at one point that norm and normalize didn't always work with complex numbers, and that seems to be actually fine to use now. So I pulled this file out. I used to have to, if I want to normalize it, I was always in the habit of doing the square root of the dot product of the vectors, because if I had complex numbers, you have to worry about the complex conjugate. And so that's what I did here. But I went and played with normalize, and normalize works. And then I'll leave it in this book when I post it. It actually also worked when the numbers were complex. And the only problem with it is the usual problem if I have variables x and y that I know are real, and I'm going to use normalize, I need to use complex expand. Or otherwise it'll think x and y are imaginary. So to just look at that real quickly, if I don't So if you look at the difference here, if I take my x plus iy1 vector and I use normalize without complex expand, I get a bunch of these absolute values left inside, because it doesn't know that x and y are real. But if I do complex expand and I tell it to do in terms of the real and imaginary parts, I get what I expect. I'm normalizing by the 1 plus x squared plus y squared. Any questions on that?